Hi everyone. So today we're going to talk about Jensen's inequality. Now, Jensen's inequality is a really cool thing, and it involves a little bit of calculus as well that you should know. But it's actually very simple. It's actually very trivial. You just need to know a little bit of derivatives. And this inequality was actually introduced by this Danish mathematician called Johan Jensen in the year, I believe, 1906. So it's been around for a little bit, and we're going to see a question. We're going to obviously learn what the Jensen's inequality is, how we can apply that, what is the aspect of calculus involved over here, because there are really two cases that we need to discuss over here. And then obviously we're going to see how we can employ this inequality in a problem and how this actually makes our lives really easy. And it's actually a very beautiful inequality. So let's just get right into it. This is the problem number 1 from the Balkan Math Olympiad in 1984. And a cool little fact, this is actually the first ever Balkan Math Olympiad problems. 1984 was the year in which this contest was started. So this was the first problem that appeared on the Balkan Math Olympiad, right? First year, first problem, and we're going to solve it. So like I said, this is the first ever BMO problem, and we're going to discuss the Jensen's inequality. Of course, a little bit about concave and convex functions. Like I said, slight application of calculus. However, that is very simple, so you should be able to follow, no worries. And then obviously we have book sessions for senior math Olympiads, and at the end, a similar but challenging problem.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
Hey, so what is its data? So quite a bit to unravel over here. You know, it looks very weird, it looks very nasty, but believe me, it's actually not that bad if you figured out a couple of things, right? So they've given to us that alpha 1, alpha 2, all the way up to alpha n are real numbers, right? And the sum of those numbers is equal to 1, right? Which is very fascinating. So just alpha 1, alpha 2 is, some numbers, real numbers, alpha I, and all of them, when you sum them up, you get to 1, right? And I should probably mention that this is actually positive reals. Okay, so they are positive reals and they sum to 1. Okay, amazing. And I need to prove this given inequality. So like I said, there's quite a bit to wrap around over here, but let's just see what is going on. Let's see if you're able to form certain patterns or actually notice what the general term or what exactly is going on over here, right? So, okay, awesome. So if you notice, in the numerator, we have this alpha 1, right? But in the denominator, there's no alpha 1. We just have 1, alpha 2, all the way till alpha n, right? Similarly, over here, you have this alpha 2. But in the denominator, alpha 2 is skipped, right? Just keep that in mind. Alpha 2 is skipped. You have 1, alpha 2 is skipped, alpha 3 all the way up till alpha n. Over here, if you just notice, alpha n, you have 1, alpha 2, it goes all the way up till alpha n minus 1, but we are skipping alpha n. That's something pretty cool, right? So there is some kind of logic going around over here. There is some kind of coherence in a way between what we're working with over here. So that could be a starting point, and it indeed is a starting point, right? Because now we can actually make certain simplifications in this, weird looking inequality and make it something that is workable. Because this in its current form is very messy. I don't like it either. This gives me a headache more than being able to solve the problem, right? So effectively, to kind of state it formally, what are we dealing with? So for example, we have alpha I in the numerator. So what is happening in the denominator? You have 1 plus alpha 1 plus alpha 2. It goes all the way up to alpha I minus 1. Then you are skipping alpha I. Alpha I is being skipped. That is the main point of my discussion. For example, alpha 1, if you remember, alpha 1 is skipped over here in the first fraction. Alpha 2 in the second fraction. Alpha n in the nth fraction. So alpha I is skipped. So you have alpha I minus 1. Alpha I is skipped. You straight away go to alpha I plus 1. And then this goes all the way up to alpha n. So it looks something like this. This is the general idea, of what's going on, right? And this is actually amazing, because if you actually notice, alpha 1 plus alpha 2 plus all the way up to alpha n is equal to 1. This is the condition given to us in the question, and this condition is not some weird looking condition that might be used. It's actually very, very helpful, and it is used in the first step itself, because if you actually notice over here, alpha 2 plus alpha 3 plus just sum all the way up to alpha n is 1 minus alpha 1. And what I can do over here is I can just replace this alpha 2 all the way up to alpha n with 1 minus alpha 1. So I'll get alpha 1 divided by 1 plus 1 minus alpha 1. Similarly, over here I'll get alpha 2 divided by 1 plus 1 minus alpha 2. Do you actually see how helpful this is? Because over here, what we've skipped alpha 2, right? So over here, just send alpha to the other side, you'll get 1 minus alpha 2. Right? And the other is obviously what was in the numerator. So 1 plus 1 minus alpha 2 goes all the way up to alpha n and divide by 1 plus 1 minus alpha n. This is our left hand side. So we have alpha 1 over 2 minus alpha 1 plus alpha 2 divided by 2 minus alpha 2 plus all the way till alpha n divided by 2 minus alpha n. And we need to prove that this is greater than or equal to n divided by 2n minus 1, right? What we have on the right hand side, n divided by 2n minus 1. So this is something that's actually very amazing. Right, so it now looks a lot simpler. Now we have gotten rid of all of these summations, and really, like I said, this condition, the first condition or second condition rather, that they're given to us, sum is equal to 1, that really helped us to reduce this, right? Because this entire thing over here that I marked in purple can be written as 1 minus alpha 1, from this condition. Similarly, this entire thing can be written as 1 minus alpha 2. Similarly, this entire thing can be written as 1 minus alpha, and then you just add 1 to this. So it becomes 2 minus alpha n, 2 minus alpha 1, 2 minus alpha 2, and the series is formed somewhat in that manner, right? So it looks something like this. Now, if I write it in summation form, how would it look? So we have this summation as n goes from, or rather I, summation as I goes from 1 to n of alpha I divided by 2 minus alpha I need to prove that this is greater than or equal to n divided by 2n minus 1. This is just writing it in summation notation so that you can get a kind of a nice closed form. And this is something that's workable. And I can deal with this. So instead of the complicated looking weird expression, alpha 1, alpha 2, skipping one part in the middle and God knows what else was there, we are actually reducing it down to something which is kind of dealable, right? Although yes, still a lot of work to be done for sure. Now, this is just a result. I'll mark that as number 1. And before we proceed further, I would like to introduce you, I think this is a good point, to introduce you to something called Jensen's inequality, right? You notice I didn't introduce it in the beginning, right? Because why not? Jensen's inequality. It's a good place to talk about this. So Jensen's inequality essentially is something that deals with means. But it doesn't deal with means of numbers, it rather deals with means of functions. So it essentially states that f of x1 plus f of x2, just sum all the way up to f of xn, divide by n. So in a way, I'm taking the mean of the functions, right, is greater than equal to f of x1 plus x2 all the way up till xn divided by n. So this is a pretty cool way, I think, to kind of remember this, just to get the idea of it. The mean of the function is greater than the function of the mean, right? Mean of the function is greater than or equal to function of the mean. Now, notice, like I said, this is dealing with functions and not with numbers. So there is a possibility that this inequality is only applied in certain circumstances, in certain situations. And that is true. This inequality is true only for convex functions. So where f is convex. So, okay, f is convex. What does a convex function mean? Convex function means that its double derivative is always positive. Its double derivative is always positive. That's essentially the definition of a convex function. Convex function is essentially, just mathematically speaking, without going into the geometrical interpretation, mathematically speaking, if a function is convex, its double derivative will always be greater than 0. Now, obviously, there are two kinds of functions. Either the function is convex or it is concave. What if it is concave? Well, if it's concave, the sign of the inequality flips. It becomes this, right? So effectively what I'm trying to say, you have the less than or equal to for concave and greater than or equal to for convex, right? So effectively greater than or equal to if f is convex, and we have less than or equal to if f is concave. So essentially, just to kind of recap that, same inequality, everything is same. Left hand side is same, right hand side remains same. Just you have this greater than or equal to inequality over here if the function is convex, and similarly you have a less than or equal to inequality if the function is concave, right? Now, like I said, a function is convex if its double derivative is greater than 0, and it is concave if its double derivative is less than 0. As simple as that, and if its double derivative is 0, you get an inflection point, but let's not talk about that. But if f is convex, then essentially it is double derivative greater than 0. If it is concave, its double derivative is less than 0. So you need to know a little bit of derivative, just calculation, derivative is something they can really compute. And the sign of the inequality depends whether the function f is convex or it is concave. And it's pretty simple, right? In terms of convex, it is greater than or equal to. In concave, it is less than or equal to. Just figure out whether the function f that you're considering is convex or concave, and then you apply the inequality, right? As simple as that. And that's actually pretty cool. So yeah, now let's return back to the question. But before that, you might ask, why does this happen? Why is the sign of the inequality changing, whether if it's convex or concave? So if I were to say it in brief, if a function g is convex, then minus g would be concave, right? Effectively, if you multiply it by minus, the concavity essentially changes. If it's convex, it becomes concave. If it's concave, it becomes convex, right? And it's like when you multiply by a negative sign, the sign of the inequality flips around. So it's kind of that logic. The sign of the inequality is flipping around because if g is convex, then minus g is concave, right? That's effectively what's happening, right? And that is why the sign of the inequality is flipping. But just remember that it's greater than or equal to for convex and less than or equal to for concave. And that's pretty much it. Okay. Now let's get back to our result. So let me just write this down actually. It's better, I guess. So we have the summation from I is equal to 1 to n of alpha I divided by 2 minus alpha I greater than or equal to n divided by 2n minus n. Mind you, this is what I have to prove. You know, this was my result number 1. Or rather, I need to prove this. Right? Till now, I haven't done any proving work. I have just simplified down the expression and then I explained to you what the Jensen inequality is. I actually haven't proven anything. This is something that I need to prove right now. Right? And to prove that, I'm going to define a function. So let f of x equals to 2 divided by, or rather not 2, maybe let's call it x divided by 2 minus x. And really the intuition, we have this alpha I over here. And we have this alpha I and we have this 2 minus alpha I over here, right? So really the intuition is replaces alpha I with an x. So in a way, f of alpha 1 will be equal to alpha 1 divided by 2 minus alpha 1, right? Similarly, f of alpha 2, plugging x equal to alpha 2, will get alpha 2 divided by 2 minus alpha 2. This is the intuition, if you're kind of getting what I mean over here. Similarly, f of alpha n is alpha n divided by 2 minus alpha n. So that is why I define the function in this particular manner. And if you actually notice, this 2 proof or this number 1 inequality is nothing but f of alpha 1 plus f of alpha 2. So alpha 1 divided by 2 minus alpha 1, alpha 2 divided by 2 minus alpha 2, sum all the way up till f of alpha n. And I need to prove that this is greater than or equal to n divided by 2n minus 1. This is amazing because, so essentially I defined the function. Right? I defined a function, that is why I'm able to write this in function notation. Right? Because before that we just have the fraction. So now actually we have a function that we're dealing with. So if I just divide by n on both sides over here, f of alpha 1 plus f of alpha 2 all the way up till f of alpha n divided by n is greater than or equal to 1 by 2n minus 1. Again, just to kind of tell you, this is, I have to prove this. I haven't proved anything. I'm just doing a little bit of simplifications here and there so that I can get along somewhere. And we have actually reached somewhere. If you just notice the left hand side, what is the left hand side? It's the mean of the function. Mean of the function. Does it remind you something? Yes. Well, a few minutes ago, we talked about the mean of the function. The mean of the function actually is the left hand side in Jensen's inequality as well. Right? If you look, you're summing over all of the f of xi's and you're dividing it by n, in a way the mean of the function. Right? Similarly, over here, the same thing. So I can say it by Jensen's inequality. I know, but here's the thing. We first need to decide whether this function is convex or concave, right? We first need to determine whether this function is convex or concave, because if it is concave, then the sign of the inequality would flip. Here, this inequality that I wrote, this is for a convex function. So the function that we have defined over here, I need to first check if this function is convex or if it is concave, and then only I can apply, right? So let's first just check that quickly. So f of x is x divided by 2 minus x. Now, just to remind you, we need to check double derivative, right? We need to check the sign of the double derivative. If it is greater than 0, less than 0, equal to 0, right? So I'll just spare you some work. You can easily calculate this by the quotient rule. So I believe f prime x becomes 2 divided by 2 minus x whole squared, and really f double prime x becomes 4 divided by 2 minus x whole cube. So well, we have this cube over here. Now, if you just notice, f prime x is greater than 0 for all values of x because we have this squared quantity. But when we talk about the double derivative, it is obviously a cubic quantity. It can be greater than 0, less than 0. You can never really tell anything about its nature. But you know what's the best part? The best part is they've given us a condition in the question, actually a couple of conditions, that it is positive reals and they sum up to 1. So basically all xi's, in a way, all xi's are positive reals, and when you just sum all of these quantities, let's say x1 plus x2 all the way till xn is equal to 1. What does that mean? That any xi needs to belong from 0 to 1. Right? So this notation. All the xi need to belong from 0 to 1 because they, for example, 0.1, 0.15, 0.25 and so on and so forth. And you can add all of these quantities and at the end you will get 1. You don't know how many of them, there are n quantities of course, but summation of all these n quantities is 1. And they are positive real entities. They are positive real numbers. That means that they have to be from 0 to 1. And if any x is between 0 to 1, that means 2 minus x is always greater than 0. So means 2 minus x whole cube is always greater than 0. That means 4 divided by 2 minus x whole cube is always greater than 0. Therefore, f double primes x is greater than 0 for all x belongs to positive reals as given the question. Therefore, f is convex. You see how amazing that is? This little information in the beginning of the question, this positive reals and this summation to 1, it is so helpful. We had to use it twice, and that small looking thing, that's actually quite fascinating, isn't it? Okay, so now that we have proved that it is convex, now we can apply Jensen's inequality over here. What I marked over here, let me just write this down again. So equation number 3 or result number 3, we had f of alpha 1 plus f of alpha 2 all the way up till f of alpha n divided by n is greater than or equal to 1 by 2n minus 1. This is again to prove. This is the thing that I marked as number 3. Again, to prove. But now that we know f is convex, right? Therefore, I can use Jensen's inequality, right? So using Jensen's inequality, and just to remind you, because it is convex, we have the greater than or equal to sign. That is effectively the reason why we're checking it, right? Why do so much hard work? To know the nature of the inequality, right? So for convex functions, you obviously have f of x1 plus f of x2 all the way up to f of xn divided by n, which is the same as the left hand side of result number 3, or other inequality number 3 is not a result, is greater than or equal to f of x1 plus x2, all the way up to xn divided by n. So in a way, again, the mean of the function is greater than the function of the mean for convex functions. Okay, awesome, right? So therefore, this entire thing on the left hand side is what we have on the left hand side over here as well, right? So therefore, since this left hand side is greater than or equal to the function of the mean, it suffices to prove, that this quantity is greater than or equal to 1 by 2n minus 1, right? So it suffices to prove f of x1 plus x2 all the way up till xn divided by n, the function of the mean is greater than or equal to 1 over 2n minus 1. Now, x1 plus x2 plus all the way up till xn, this was given to be 1. So really I can write this as f of 1 by n is greater than or equal to 1 by 2n minus 1, and this is what I need to prove. Like, just to remind you, I haven't done any actual proving yet. I've really only simplified things down, and this I need to prove. Now, again, just to remind you, f of x, what was it? X divided by 2 minus x. Well, what is f of 1 by n? It's easy to find. Just replace x with 1 by n. So 1 by n, 2 minus 1 by n. So f of 1 by n, lo and behold, this actually happens to be 1 by 2n minus 1. Wow, that was fascinating, right? So f of n is actually 1 by 2n minus 1. So this is true. It's greater than or equal to. In fact, it is actually equal to. So f of 1 by n is actually equal to 2n minus 1. Right? So therefore, f of alpha 1 plus f of alpha 2 all the way to f of alpha n divided by n, which is greater than or equal to this function of the mean, is actually also greater than or equal to 1 by 2n minus 1, because the function of the mean f of 1 by n is equal to 1 by 2n minus 1. So this is greater than 1 by 2n minus 1, and effectively we have proven the result. So therefore, what was this? Just replacing this f of alpha i's, you will get summation from I is equal to 1 to n of alpha I divided by 2 minus alpha I is greater than or equal to 1 by 2n minus 1. So I'm just going in reverse order now that we've proven this. It's just going in reverse order, replacing the function back with what it was in the original, because now this is something that we have proven. Earlier, it was simplification Earlier it was modification and simplification. Now that we are proving it, now that we have actually proven it, you go back in reverse direction to prove the original result. So this was the original result, the original thing that we had to prove, and hence we have proved it. Right? So quite an interesting question. Really fascinating actually. So just remember the Jensen inequality actually depends whether the function is convex or concave. And once you actually got down to this result, once you actually kind of saw something like this, saw something like of this form, and then you actually saw that it could be denoted in function notation by letting this function x or 2 minus x, and then you actually got this result, equation number 3. Equation number 3, or rather this point number 3, whatever you might want to call it, is where it kind of pivoted. Right? Is where that you clearly see that, okay, you can apply Jensen's inequality over here, because you have this mean of a function kind of a thing over here, and mean of a function is greater than or equal to function of a mean, which is the interpretation that you can use to remember Jensen's inequality. Right now, obviously it differs for convex and concave functions, and we clearly saw that this function f is convex using the cheeky little conditions that we had given us originally in the question. So all xi's are between 0 and 1, therefore it is convex, and we wrote this Jensen inequality, and it so happened to be that all of these f of 1 by n is actually equal to 1 by 2n minus 1. Right? It is actually equal to 1 by 2n minus 1, which you had seen over here, and then after that we're just going backwards, and hence we have effectively proved our original result. So I really hope you like that, hope you learned something from that, and that was a pretty cool discussion of Jensen's inequality. Okay, so moving on to certain book suggestions for senior math Olympiads. I am a compendium, Polynomials by Parpeyu, Elementary Number Theory by Sierpinski, Graph Theory by Harari, Combinatics by Probability, Secrets in Inequalities, and Functional Equations How to Solve Them by Christopher G. Small. Okay, so we have a couple of questions for you. So first would be proving the AMGM inequality using Jensen's inequality. This is something I really like to do myself as well. Or try proving AMGM inequality using the techniques that you might know from other inequalities. Maybe try proving it using Cauchy-Schwarz, maybe Tito's inequality, maybe Holder's, maybe rearrangement, maybe Jensen's inequality. And just prove these inequalities in different ways using other inequalities. That's actually pretty cool. It's a pretty cool exercise. And then if you're able to do that, maybe try proving the second inequality. It's actually also quite fun. Right, and IMO problems have also been based upon Jensen's inequality, although I don't think number 2 is an IMO problem, but maybe just try it out, and if you're able to do it, let me know. Until then, I'll see you in the next video. Thank you very much, and bye-bye.
Cheenta programs are designed for students who are passionate about mathematics, and they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.